Math 2414, Partial Fractions, Video 9, Example of Unique Quadratic Factors. I know this seems like a lot of videos and they just don't seem to stop, but if we just talked about the technique of integrating using partial fractions from a super generic perspective, I would be leaving out a lot of these specific situations that call for different analysis, different moves, etc., etc. It is possible to summarize the technique of integration by partial fractions in one gigantic statement, but being introduced to the technique, I don't think that would do it justice. So yes, and just to let you know, there is a case for, and then we'll start wrapping things up. All right, let's integrate this guy. The integral of 2x squared minus x plus 4 over x cubed plus 4x dx. Being a rational function, we want to think about integrating it using partial fractions. It does meet the degree requirement. The degree of the denominator is greater than the degree of the numerator, so we don't have to do any long division. However, we do want to factor the denominator because in order to do a partial fraction decomposition, you have to know the factors of the denominator. At the very least, you could factor out an x from the denominator since it is a common factor, leaving behind an x squared plus 4. But a sum of squares is prime, and therefore that is an irreducible quadratic factor. Hey, it's the fraction we did the partial fraction decomposition on in the previous video. So from the previous video, we already know what this decomposes into. This decomposes into, I lost it, there it is. This decomposes into 1 over x plus x minus 1 over x squared plus 4. And again, it was quite a bit of work between the pre-decomposition and the post-decomposition into partial fractions, but let's use the result that we built from the last video. And now let's talk about how to integrate this. And by the way, as a partial fractions issue, that issue has been solved. Now it's just calculus 1, maybe a little bit of calculus 2. The first integral is going to be pretty transparent. Let's go ahead and split it off. But the second integral might not be as transparent because we're still integrating a fraction and we really can't do a decomposition on it because its denominator won't factor. So how can we integrate this? Substitution, do a trig substitution, God help us. The answer to both of those is we could, but here's a little trick that's very handy to know. If you are integrating a fraction, the denominator is x squared plus a number, like this, then you might be better off splitting this into two separate fractions, each with the same common denominator. In other words, let's split this into x over x squared plus 4 minus 1 over x squared plus 4. And you might be thinking, why would we want to do that? Now we have two fractions instead of one. Well, honestly, let me get this cleaned up. There we go. Honestly, these three integrals are all pretty straightforward. Let's move them to the next page and then tackle them one at a time. The first integral is just the natural log of the absolute value of x, so there's not a whole lot to see there. What about the second integral? Let's take it out to the side here. Integral of x over x squared plus 4. You might be tempted to try a trig substitution, like x equals 2 theta, and that would eventually work. But as you're deciding an integration technique, you should always think about your choices in the same order, beginning with a u substitution. And in this case, a u substitution would work fine. We let u equal x squared plus 4, then du would be 2x dx. And we can build this du package pretty easily. Dx clearly is there, the x is there, the only factor missing is this constant factor of 2. So we could put a 2 in there, balance it with the 1/2, and now we're ready to do our substitutions. 1/2 integral, the 2, the x, the dx all become the du, everything in the numerator got consumed into the du package, so 1 is left in the numerator, and the denominator becomes u. This is just a natural log, 1/2 natural log absolute value of u, but u is representing x squared plus 4. So let's move that into our answer. 1/2 natural log absolute value of x squared plus 4. Now, I'll be honest, in this natural log, the absolute value is redundant because x squared plus 4 is always positive when x is a real number. But what about the third integral? What about this guy? Could we do a trig sub? Yeah, we could say x equals 2 tangent theta. Could we can't do a partial fraction decomposition because x squared plus 4 is a factor. Could we do a substitution? No, because we did the substitution on the previous one and needed the x. There is no x in this one, package. However, we actually have an integral rule. The integral rule was the integral of 1 over x squared plus a squared dx is equal to 1 over a arc tangent x over a plus c. Which, by the way, is what you would get if you did a trig substitution. But if you know this rule, and seriously, you should know this rule, because I don't want you to have to reinvent how to integrate this type of fraction every time you run across it. If you don't know this integration rule, stop the video, write it down, say it 100 times or however many times until you know it, so that you don't have to panic every time you run across it. All right. So we're going to use that rule to evaluate the last integral. Let's get rid of the second integral's work because, frankly, it's kind of in the way. All right. And now let's evaluate the third integral. The third integral is following the rule that I just wrote on the bottom with a equal to 2, since 2 squared is equal to 4. So minus, that was in front of the integral sign right there. 1 over a, but a is 2, arc tangent of x over a, but a is 2, plus c, and just like that, it's over. And there's our answer. So let's just quickly review what happened after the partial fraction decomposition. Because the partial fraction decomposition, in other words, getting it down to this point here, getting it down to, whoa, hold on folks, things are going a little bit crazy. All right, getting to the partial fraction decomposition here, that was probably the more challenging part of this, which was done in the previous video. But the other move, which may or may not be in your arsenal, but needs to be in your arsenal, is knowing that you can split a fraction like this into these two fractions, then integrate them separately. But there is our final answer in it.